One of the properties that depends on temperature is actually length or volume, and we call this thermal expansion. And the idea being that if we increase the temperature and we're measuring the length of, say, a metal rod, we see that its length increases. Now, this is interesting for a few reasons. One, this is actually a way we can measure temperature. Different metals expand at a different rate, so there's something called a bimetallic strip, which actually curves as you heat it because you've put two metals on each side, so it actually curves to the side as it's heated, and that can make and break electrical connections. It's a simple way to make a thermostat. Now, a second way that we can use this to measure temperature is actually a thermometer. Now, a thermometer is actually about a change in volume because there's a small ball at the bottom that contains our liquid. But if you imagine that this is really just about length, as you increase the temperature, the length of our liquid gets longer. It goes up the scale. So that's really how a thermometer works. We're changing the length of a liquid, or truly the volume, and then we've just plopped down a numerical tick mark next to it that has been calibrated to tell us what the temperature is. So thermal expansion in itself is important because it shows us one example of a property that depends on temperature, and it's a really common way we turn around and then measure temperature. So every material is going to have a linear expansion coefficient and possibly a volume expansion coefficient, depending on the type of material. So if we're talking about metals, those can basically be made into wires that then you imagine changing length. And in this case, the proportional change in length, so the amount that it's changed over the original length, is going to be some constant, again you have to just look that up in a table, multiplied by the change in temperature. Ideally, you would do this in Kelvin, but remember that once you have a change in temperature, it is the same in Celsius. So note that this says Celsius to the -1, meaning this is per degree Celsius. So you can multiply your temperature change in either degree Celsius or Kelvin. It's good to be in the habit of always thinking Kelvin. If we have a liquid, it doesn't really make sense to talk about its length. Again, you can shove it into a straw like volume such that it has to change length, but otherwise it's going to just naturally change in volume. And so we use alpha for linear and beta for volume just to make it clear that they're different coefficients. But again, the relationship between the change in volume and the volume looks very similar. Note that on the left, your units will cancel because you have a length divided by a length, so your units cancel. Here you have a volume divided by a volume. So similarly, your units need to cancel on the right side of these equations. Now, if you have something like a solid, where you imagine that it actually is changing in length on every single side, and the book goes through this derivation, that these solids would still have a volume expansion coefficient, but in this case, the volume expansion coefficient is just 3 times the linear coefficient. And again, the book goes through that calculation.